Hey, I'm Whitney. I'm a hardware engineer from Facebook. I'm in charge of Facebook AI machine learning system design. And Richard.
I'm Richard. I'm from Baidu. I'm responsible for the Baidu AI computer and also the distributed training platform.
And I'm Siamak Tavallaei. I'm a platform architect with CSI Azure Microsoft.
Okay. So let's just start. As Siamak just mentioned that today we're going to have two sections. So this one, we will talk more about the system level when we have a module, right? And then what we do after this module, and then what's the plan so far. And then 3:30, we have another session that is more specifically for this Open Accelerator module. We're going to more detailed discuss and also introduce about the module itself, how we define the spec. Electrically, mechanically, and thermal side. For this session, we more focus on the system level and then the infrastructure level, how we create a platform for this area. We're going to talk about the motivation and approach, and then we will have some examples to show you why we're doing this. And then more importantly, we invite the community to join us and to move this together. We do need some common form factor, and then we will talk more about this. So, like recently, couple years, AI has been exponentially growing. I did a check with one of our TPM that how many accelerator company are there? And then my answer is 45, at least we know. 45 companies, the big giant companies and then the small startups. As we know, there are 45 companies, they create different kind of accelerator. There are so many chips coming out, and then all of them, we need to make some form factor and then implement to our system. But which one we want to use? We want to use the best one. So here we are. There already, in the market, there are already many different kind of form factor with the module, with the card, and then we just need to build different kind of system and implement them together. So we see, here is a picture that the left side is Facebook's different generation of AI platform. The middle one is from Microsoft. And then the right one, we have a Baidu system. So we are doing the same thing, but we create so many different kind of systems. So that's why we are together, and then to sit down to see what we can do to commonize all this implementation.
Okay, so
go ahead.
We just see that we have a lot of different implementations, but generally they are targeting the similar requirements. So for typical AI hardware, this one. For a typical AI hardware system, so what's the necessary components? So generally, first you need the accelerators, and you need a baseboard that hosts them. And you also need a CPU load to control the accelerators. And generally, the CPU load can support generally just the 4 accelerators. So you need the PCI switch to connect the accelerators and the CPU load. So these 3 parts can be combined together physically in one chassis for easier implementation. Of course, you can also disaggregate them to make it as flexible as possible. And so to support the system, you also need some basic infrastructures. That is the power and the cooling. The power can be distributed or it can be shared. And also for the cooling, it can be a central fan or it can be a distributed fan. It can be air cooling or it can be a liquid cooling. So, and what makes the AI hardware system that is different from a traditional servers is that it needs high bandwidth between the accelerators to scale up, scale down, and also scale out. So within the chassis, the baseboard topology is very important. And also you need some kind of high-speed expansion links, some other proprietary, to scale out the system. And also you need of course you can use the RDMA fabric to scale out. And also you need that to feed the data into the systems. So it would be ideal that we can combine all these logical components as whatever you want to make it as flexible as possible as scalable as possible, as efficient as possible. Yeah. Okay, let's look at some examples. Yeah, these are accelerators in the PCIe form factor. This is the most typical AI hardware system in our data centers. Right? But for this system, it's quite difficult to support high-speed interconnection between the accelerators. So if you want to do that, okay, it will become non-standard. So then this comes the mezzanine form factors. Yeah. On the left side, this is Microsoft HGX1, and in the middle is Facebook Big Basin, and on the right is Baidu Xman. The upper one is the second generation that can support 8, and the lower one is our third generation that can support even more than 16 accelerators. And also, yeah, we mentioned that the topology for the AI hardware system is very important. Yeah, actually, these different three systems are targeting the similar, are supporting the similar accelerators, and the topology between them is almost the same. But what is quite different is that the collection, the topology between the accelerators and the CPU load is quite different. It's just that, we don't talk with each other, and maybe we have some our own requirements, but we think that we should have a common way to build this. Yeah. And so for the power and generally, currently most GPU servers has the power supply unit integrated with the chassis itself. Yeah. And you have other ways in the purse. Yeah, so you can also have a shared power, for example. Yeah, in the middle, this is a Facebook Open Rack. It's a shared power, and there is a bus bar to distribute the power. And on the right, this is a Baidu Rack. So it also has a shared power and also the bus bar architecture, but the location of the bus bar is different. And for the cooling method, so generally there are two ways. One is air cooling, the other is liquid cooling. So currently most GPU servers has the fans physically located in the chassis for easier implementation. And the other way is that you can disaggregate the fans from the computer load and the GPU load, the accelerator load, to a central way. So yeah, on this example, this is a shared firmware. And also you can use liquid cooling to support accelerators that with more than 400 watts. So that would be can solve the thermal challenges. Yeah, okay. And for the management, yeah, if you are deploying a large scale of servers in the data center, so the remote monitoring and automatic management is very important. So to standardize this module, the management module is very important. Next. Okay, and so for the I/O board, so here I/O means networking I/O, storage I/O, and also the I/O between the CPU and the accelerators. So the I/O board should be as flexible as possible so that it can support different scenarios as you required. And there are also some MISC I/Os. So it's the LED, the button, and management port. So it's better to standardize these systems. Yeah. So yeah, we see a lot of examples, right? So generally, these different implementations are actually solving the similar problems. So the typical one is that the flexibility, the reliability, and easier management. These are general requirements for the data center servers. But what makes the AI hardware system that is quite different is that the AI accelerators has very, very big power. So it will make the power and cooling in the system design very challenging. And the other difference is that the AI accelerators should support high-speed interconnections to make sure the bandwidth and is very big, and also the latency is very, very small. So the intermodule communication is very important, and also the bandwidth between the chassis is important. So basically, the AI hardware system should have the ability to scale down for small workloads, scale up for middle workloads, and scale out for even bigger workloads. So how you will do to solve this kind of challenges? So after Baidu, Facebook, and Microsoft, we talked with each other. We think that this is the right time. We should find the right way to build the AI hardware systems. So now let's Siamak share what we have done.
Okay, so as we just heard, Zhao, there are different ways of doing a good system, and we have learned how to do that going fast and doing it individual work. And now we realize that doing it second generation, third generation, we can do better together. So open together is a theme with OCP Summit this year, and that's what we're here to demonstrate, that we can actually make a better system. So we basically need an open infrastructure model to help us work together. If we do that, then we can increase the interoperability of different modules. The modules, as you saw, could be power modules, cooling modules, compute modules, chassis, mechanical. This is to accelerate innovation. So different modules can be designed independently, but then combine to create a better system. So we started with the definition of the OCP Accelerator Module itself. We realized that PCIe CHEM form factor was not complete. We chose the OCP Accelerator Module connectors so that we could increase the number of inter-module links. We wanted to go fast, so we picked a high-speed interconnect capability. We wanted to have enough space for all the cooling and voltage and power distribution to the module. We wanted to have a flexible heatsink for either air-cooled or liquid-cooled systems. And of course, we wanted to have a very good module-to-module interconnect for different topologies, for different neural networks. So aside from the module itself, the system is not complete. We have to complete the story. So what we did was to form a group. We are here together, and we're forming a subgroup to work with you guys to go beyond just the OAM itself. So we are proposing to build a baseboard, a universal baseboard with different interconnect topologies possible. A tray so that physically things can move from one chassis to another. Build the whole chassis so different chassis can support different trays can support different baseboards can support different modules can support solutions from different companies. And of course, we need to put them all together and manage them in a secure model. So we will have, as part of the specification, a management and security framework as well. So we're trying to do everything in a modular way. So we start with a base specification. Within the base specification, we will have logical blocks and physical blocks. Power and cooling, mechanical, electrical, and security management can be thought of as being logical blocks. And for the physical entities, we have the OAM itself. We have a universal baseboard for the interconnect. Again, tray as a modular element for serviceability and management. Individual companies can build solutions that can be compatible and interoperable by supporting these specs. One solution can support all, but there could be variations as well. As I said, everything's in a modular way. So we have a base specification. That's what we do at OCP Server Project. We have normally a base specification that defines architectural concepts. And then we have a design. Multiple designs can come from the same base specification. And off of the detailed design, multiple products can be built from different companies, and we put them on the marketplace. So the universal baseboard is the one that provides the multiple interconnects. And perhaps Richard can tell us about it.
Yeah, so we mentioned that interconnection bandwidth and also the topology between the accelerators is very important, because different neural networks and different framework implementations actually have different mechanisms. And also you are training the system in a model paradigm or in data paradigm, that's quite different. So all these kind of applications have a kind of dependency on the interconnect topologies and also the bandwidth. So then how we can solve this kind of challenges so that we can support different kinds of accelerators and also different kinds of applications more efficiently. So here, there's a universal baseboard. So for suppose on this picture, you can see that so suppose there are 8 accelerators and there are baseboards that hosting them. So to make it universal, the form factor of the baseboard should be the same, it should be standard so that it can be tailored. It should be used in most scenarios. And also, the connection between the accelerators should be kind of transparent. So the connection between them, there are kind of wires between them, but the wires should be just wires, right? So it should be agnostic to the protocol that running on this. For example, you can have a CSX, or you can have MLink, or you can have any other high-speed interconnection. It's proprietary, but it doesn't matter. It's just logical, right? So the physical is the same. Yeah, it can support different kind of protocol running on this. So suppose this is kind of, there are different kinds of topologies. Here you can see this, if the accelerators has limited links, for example, 4, so it will be most typical that you can have a 3D mesh connect the topologies within the chassis. And also you can have some kind of high-speed connection between the chassis to allow it for expansion. And if you have the module that with 6 links, then you can create a 3D mesh or torus or high cube mesh topologies. And if you have the accelerators that with 7 links, you can create fully connected topologies. But the connection between them is point to point. So it's a little difficult for the solver. And of course, you can add a central switch to connect all the accelerators. Yeah. So in this way, this can provide the maximum bisection bandwidth. And there's only one hop between any accelerators. And also the switch is kind of lamp blocking, and it also allows for expansion. But the most challenging for this topology is that actually you cannot design a very, very big central switch that can support a lot of accelerators with a lot of links. That's not possible. So there's some workaround here. Yeah, for example, in this picture, you can see that all the accelerators are just connected to kind of switch, but this switch is kind of smaller. It has limited links. Yeah, so it is also one hop away. It can also achieve the maximum bisection bandwidth. But the difference for this system is that actually each accelerator communicates with each other just with one link. Yeah, if the switch itself has ability to combine all the switches together to make it a single logic switch, then it will be easier for solder. Otherwise, the solder implementation will be quite different. Okay, so we see a lot of topologies. So this kind of topologies has kind of dependency on the capabilities of the accelerator itself. And also, even with the same accelerators, the topology can be different. Yeah, just because the different applications has different kind of dependencies. So we are trying to build a universal baseboard that is flexible in most scenarios. And besides that, actually, this kind of baseboard can support heterogeneous accelerators located in the same chassis. Yeah, it has the same, it's the same form factor in the system, and each different accelerators can carry out a different task. For example, in the video streaming scenario, typically the video should be decoded and do some pre-processing. So this is not the right job for most accelerators. Then you can have a transcoder, right? Encoder, decoder, in front, and after the data is processed, you can pass that data to the next hop for the real AI accelerators to do the AI-related work. So it can work together in a pipeline way. So that can help the system to work more efficient. And so this is something what high level, right? We have the base specification. We have different kind of topologies, yes, with a unified baseboard to support that. And let's see what we have done now. Yeah, let's Whitney share the OAM spec.
We may run out of time, so I will go really quick about our current OAM. Since we will have a 3:30, we will have a specific session to talk about the OAM spec. This is a high-level spec. The current, so yesterday we already officially contribute the design spec into OCP community, so you can all download the spec. We have a 3D file, we have a heat-sink design examples, design files, and also the pin mapping detail spec will all contribute to OCP already, so you can download. Just some highlight for here. It's 1.2 by 165 millimeter, like this is the size, and then we have a heat-sink design. This is we designed this sample to Facebook project. We enabled one of the project from yesterday keynote. You may see that. So this is our baseboard design. Then we have 8 of them. In the system, and then we connect them in a fully connected way. Depending on which OAM or module we are using, that maybe become different topology. So OAM, we support both 12 volt and 48 volt, and for up to 450 watt, we can use air cooled, and beyond that, yeah, based on the thermal simulation we made, that I think we need to go liquid cool. So this is a heat-sink. So after the session, you can come to our booth or here, you can check out the design. 3:30, come back to us. We're going to talk about the spec itself in details. And also, if you want to get the link of this talk, and then, here is a link to get them.
The OAM session is at HPC track. So this is the server track that you are here. So infrastructure was the main topic today, right now. At 3:30 at HPC track, we will have detailed discussion on the module itself. We have a little bit of time for questions if you guys ask. Thank you, John.
Yeah, there's 2 microphones. If anyone has a question, come to the microphone or get this one. Questions, anyone? Wow, you almost have done a really good job.
All right. Awesome.
Just a quick question. I would love to hear more about the pipelining and the heterogeneity and the sort of the vision there and how that pipeline plays out. Is that in scope for the few remaining minutes?
We are also very interested in hearing your thoughts about that.
I mean, I'm a very imaginative guy, but I don't have a vision for how it works. But I guess my biggest question was, should that be part of the spec and alignment?
That's a very good question. So at a high level within the solution space, it should be part of the discussion. But as part of the hardware development, that will be beyond the hardware development. Right. As an example, you can imagine that neural networks have multiple layers. It is likely that certain layers are suitable for a different kind of acceleration. So you can think about running the program through multiple layers and chain them together. One of the reasons that ring networks are suitable is for those kind of transfers. So parameters might change from one stage to another stage, and each stage can have a different processing element. The other methods are more uniform, and maybe a fully connected mesh is a better solution. You exchange parameters very similar to MapReduce, for example.
Thank you.
You're welcome.
So how do you define the universal baseboard without knowing what the accelerator itself is?
A modular design, the thought behind modular design is that we don't need to know what the future is. We start with one reference, and Whitney offered this particular solution. That's one particular interconnect. And as we go through, different colleagues here will develop different accelerators that require different interconnect. And based on different interconnect, the topology might be different. But what we would like to create is an interoperable module. So one chassis can be built with multiple tray locations. Different trains can go in the same slot. We have basically seen that different companies already do that for themselves, for generation to generation, for saving time and development cost. They have created modules for themselves. But what we are trying to propose here, and what we are proposing hopefully to work with you guys, going from one company's solution to another company's solution, we can interchange that as well. Richard? No,
Yeah,
sorry.
so since we already started one of the project, so you can come to our 3:30 session. We're going to talk about specifically, based on the current OAM spec, what kind of topology. I mean, we have a very detailed topology and also the layout study there, and we're going to detail talk about it. So yeah, you can come back later.
Yeah, I think add a little clarification. The universal baseboard doesn't mean that it's a single one baseboard. It just means that in a architecture perspective, this baseboard in a system level should be some kind of standard to make sure, okay, you will not design another chassis, right? But the topology on the baseboard itself still allows difference because you cannot have single one for everything, right?
The spec will be universal. Individual baseboard might be unique.
Baseboard for topology, where power comes in.
That's right. Yeah.
Thank you. Thank you very much.
Thank
Please
you.
come to the 3:30 session.
See you later.
Yes. Thank you, Siamak. Thank you, Whitney. Thank you, Richard.